Hello, everybody. Welcome, welcome. Welcome all. Hope we're having a great day so far. Hope we're feeling good. It's Tuesday, December 17th, and we are back learning and putting our nose to the grind, doing our nose a little grind in some Python here. Let's let the Discord know that we are live. All right, let's go get those hairs off my computer. Okay. How are you guys doing today? Welcome, welcome. I'm super excited to talk with you guys today and learn some more Python, learn some more DSA in Python. Hopefully, move on to chapter 5 today, which would be great. Yeah, it's. I'm really looking forward to getting into this. So, we have one more problem to solve for the reinforcement problems in chapter 4. We have 4-8. So, all right, so let's go ahead and copy this guy on over. Get him loaded up into the chamber. Boom. Boom. Okay. This one looks a little this one looks a little hard, I'm not gonna lie. Oh, I'm not gonna lie, this one looks a little hard. Okay. Isabel has an interesting way of summing the values in a sequence A of n integers. So we have a sequence A with a length of n, where n is a power of 2. N is a power of 2. She creates a new sequence B of half the size of A, right? And sets B index I equal to A index 2 times I index 2 plus A and 2 times 2I plus 1 all the way for I equals 0 all the way until n minus divided by 2 minus 1. If B has a size 1, she outputs B index 0. Otherwise, she replaces A with B and repeats the process. Oh my gosh, what is this problem? I can already tell this is gonna be rough. Hello, that kid dude. Welcome, welcome. Good to hear. I'm so glad you're here today. Welcome. Um, Good to hear from you again. I hope you're doing great. So we have a sequence A. That's right. We have some sequence A, right, is equal to something. So where n is a power of 2. It's a power of 2. Hey guys, hey Michael, how are you? Have you seen a lot of UFOs? I haven't seen any in person. I I've seen the stuff on the news, but until I see something in person, I don't know. I don't know. And we have like I don't know. We have the ability to photograph like deep into space, like deep into space, but yet we can't take a stable picture of a couple of drones. Like I don't know. Doesn't seem right to me. Doesn't seem right to me. Okay, so we have some sequence A of n integers where n is a power of 2, meaning 2, 4, n is a power of 2. She creates a new sequence B that is half the size of A and sets B at index I equal to A index I 2I for If B has size 1, she outputs B at index 0. Otherwise, she replaces A with B and repeats the process. Replaces A with B. Be careful. Hey, Distracted Funny, welcome in. How are you doing today? Welcome. Okay, so how could we go about solving this one? If we want to call... What are you doing? Introduce to sum the value sequence. So we'll do def sum sequence. And right, we take in some sequence A, right? So we take the length of A and we set that equal to n, right? So we get the length of A. She creates a new sequence where n is a power of 2. Where blank is a power of 2, meaning, I don't like this word, 2 to the n, where n is a non-negative integer. Okay, 2 and 2 to the power of n, where n is a power of 2. Okay, we'll keep that in mind. She creates a new sequence B of half the size of A. B equals sequence half the size of A right? So we're getting a new sequence that's half the size of A. Yo, Lambda. Sorry, not Llama. Lambda. Appreciate you coming in. Welcome, welcome. Good to be in here. Welcome. I'm glad you're here. Glad we can connect and work on some problems here and learn some Python. Some programming. All right. Half the size of A and sets n divided by 2 minus 1. So if B if B if length B is equal to 1, we want to return B at index 0. Okay? So if length of B is equal to 1, she outputs B0. Otherwise, she replaces A with B and repeats the process. She replaces A with B. Oh my gosh. So she creates a new sequence B, half the size of A, and sets B index So we have to be able to recurse down A, right? We have to call in here some sequence for some A sequence for B, right? So you call some sequence for B, which is half the length. So we're iterating down by half each time. So this is going to have a log n power, or time complexity. I'm assuming that's just the answer to the problem here is log n, right? So we're going to call some sequence on B. And then, so we need to factor in this placing though of B values. So what is going on here? B at index I is equal to A index 2I plus A index 2I plus 1 for index is equal to 0, 1, all the way to 2n minus 1, or 2 divided by n minus 1. So all the way until, so a sequence, we'll set this portion, let's make a sequence here that's like 5, 3, 7, 8, 2, right? Let's make it just like 3 numbers. Okay, I'm not cannot go. I'm not even gonna try to pronounce that one. You got me there. I appreciate you joining though. Thank you so much for coming in. It starts with the C. Thank you so much. Okay, where do we go from here? So we need to, where n is a power of 2. How many hours do you spend for algorithms in Python? Well, so far we spent quite a lot. We are on page 202 out of 770 in data structure and algorithms. We are reading the entire book aloud here, live on stream, and working on the practice problems at the end of the chapters. And then we work on personal projects in the back half of the stream, such as the small business manager that we've been writing live on stream, where we're going to be managing items in a business, managing transactions of those items, creating cost reports, expense reports, yada, yada, yada. So, and just to prove that what we're learning here is actually being applied, is we actually wrote a binary search function in our program that we ended up refactoring out, but we were able to write that in successfully. So we are learning stuff here, and we are trying, right? Trying to at least. So we need to do this setting of B index is equal to so some sequence B so B0 gets returned when it breaks down all the way to 1. So 7 will be returned, okay? And we need to say that number 7 is equal to B gets created half the value. So we need to floor this. Right? So let's think about this. Let's pull up the old whiteboard here, guys. So if we're starting off with the sequence A, right, we have A is equal to our sequence up here, length 3. So we compute then some sequence is equal to 3, right? Okay, actually I'm gonna make this 4 for now, just so we have even numbers, right? 2 to the power of n. We have to keep that in mind as well, where n is a power of 2. Easy. Stop chasing the cat. Hey, no chasing cat. Come on. Leave the kitty alone. Leave the kitty alone. No chasing. Come on. Go lay down. Go lay down. Go lay down. Up. Come on. Okay. So we create, where were we? So we have 4 numbers in our sequence. I'm just going to say function, right? F of 3. Or sorry, 4. We had 4 now. So we are going to create a new sequence at this point, right? We're going to say b is n divided by 2, and we're going to load in sequence b, so this comes in function of 2, and this does divided by 2 is equal to 1, right? So this becomes function of 1, where now we return, right? We need to return the 7. Or no, in this case it's a 4 now, right? We return the 4. So the 4 is being returned to our previous recursion. Now the 4, what do we need to do to the 4? The 4 is being placed here. We need to take the 4 and set b, so we need to interact with this some sequence function, right? So the 4 is going to be b at index 0 is returned, right? So a at index 2 times 0, or what does 2I mean? Is this 2 times the index times the is this 2 times whatever that value is, or what is 2I in this case? Hey, leave the cat alone. Come on. No, that's bad. Come on. Stop chasing her. Sorry, guys. Gotta be a parent over here. Gotta discipline my children. Come on, leave the cat alone. She's just hanging out. Hey, Peyton, thanks so much for coming in. I appreciate you stopping by. Sorry you guys had to see that. Okay. Doing fantastic. Just got over my sickness. Time to start learning some more coding. Great. Awesome. So we need to we're returning b at index I. Outputs b index 0. Right now we're reading data structures and algorithms in Python. This is in the in my Discord, and you can find this PDF in my Discord or just online. So if we're returning 4 as this, right? Sequence B is being returning this. So like return B, this is physically 4 that's being placed back into this value here. Naman Rowit says, wow, dude, I discovered your channel a week ago and you had 200 subs. Now you're at 481. Good on you, Michael. I hope your journey goes well. Yeah, well, no, honestly, it's all thanks to you guys. You know, I just come in here and learn, and it's easy for me to sit here and learn, so I probably would have been doing it anyways. And so you guys are just showing me the support. And so it's all on you guys, really. Trust me. So like, give your own selves a round of applause, your own pat on the back. I would have been doing this anyways. You guys are the ones tuning in with your time and are also dedicating yourselves to learning. So you guys deserve just as much, applause for that. Yeah. But I appreciate your comment. Thank you so much. Ozzy, thanks so much for coming in. Okay, so what is going on here? This is the part we need to now solve. And then we also have to keep in mind this part here. So as an interesting way of summing all the sequence of A integers where n is a power of 2. Okay, so n has to be a power of 2. So what did we predetermine was a power of 2? When something is a power of 2, it means that it can be expressed as 2 to the power of n, where n is a non-negative integer. In general, numbers like 1, 2, 4, 8, 16, 32, and so on are powers of 2 because they result from multiplying 2 by itself n times. Oh, so we need to say if, like, we need to determine a, so the sequence has to be a power of 2, right? That's the only way it works. So, um, 1, 2, 4, 8, 16, 32, or so on are powers of 2 because they result from multiplying 2 by n times where n is greater than 0. So we need to do some mathematical operation on this return value, but we also need to determine if a is a power of 2. So how can we do that? We can take n, raise it to 2 to the power of n. We can modulo it, right? Modulo would give me the remainder. So I couldn't modulo divided by 2 because I would get, I need 1 is a power of 2. We'll come back to that part. So we just know that we have to have either 1, 2, 4, 8, 16, or 32 values in our sequence. So we have to factor that in somewhere into our function, I think, like a check. Um, Normally, new programmers wouldn't be able to solve problems like this even after 3 months. I guess that college background is really helping you with this one. Well, I started back in uh, May, June, so it's been about 6 months, but I've been taking it really seriously for the past about three, I guess you could say, going on like maybe three-ish, yeah, months now. So, well, I really appreciate the comment. Yeah, I do have some math background, just in my chemistry and stuff, but it's not complex math. It's just basic like arithmetic and statistics and things like that and fractions. But um, like I never have to use like powers or anything like in my current occupation and stuff like that. Um, but I took calculus back my freshman year of college. And then I that was like the furthest I went in math was calculus my freshman year. I took a higher level 3000 statistics course my junior senior year, but um, yeah, but calculus was as high as I went. Okay, so anybody have any ideas about how we're supposed to what we're supposed to do with this? So we're supposed to the value that gets returned be at whatever index. So if this is 0, we have to say a is 0 because are we saying 2 times 0, index 0? Or what does the 2i mean? So if the I is 0 in this case because we're returning b at 0, right? Are we multiplying the value at a? No, I think we're multiplying 0 by 2. So this we would just retrieve a0. So we need to say the sum of the sequence. So this returns b0. So if b is 0 in this case, we need to sum all of the values up to but this would just be at that one index. So we need to add to it a variable. So we would take, we return sequence B, right? Oh, I'm getting there. I'm feeling. I can feel it. I can feel it. I'm getting there. Maybe I'm not, but I'm trying to get ahead of myself. Okay. So we returning sequence B. So B0 is returned. So which is going to be this value. Oh, I'm confused on which side is which. Like which one is the return statement? So it sets B at index 0 in this case because we're returning B at index 0 as, so this is B as index 0 is equal to do I say A um, so A 2I. So what would be 2I here? Oh, this is interesting. Okay. Hey, Chase from space. How you doing? So we're returning 4. What are we doing to 4? We are setting 4. So she outputs B0 and repeats the process. B0. So B at 0 would be this. Right? So what do we, at this step we are creating, we have a sequence of A4 and we have a B2. At this sequence we have a B1 and at this sequence we have a B divided by 2, 0, right? So we get returned at this stage. We have a B with the size of 1. Well, at this stage, B is the size of 1, actually. So we return at here, not here. No. Let's go back. So we call function of A, which is 3, or in this case 4. This recurses down and calls function of B2, which sets B2 to A in a sense. So we set B to 2 and A becomes, then B2 becomes here and becomes A2 and we set B to 2 divided by 2 is 1, so b becomes 1. Okay, length of b is 1 now. So at this stage, A2 then b is half. Okay, so sorry guys. A index I times 0 plus a index I times 0 plus 1, and so on. This returns b at index 0, which is technically now our into our a. So n at this case would be 1. So plus, is it n plus some sequence b? So this would be 5, 8, 15, whoops. 5, 8, 15, 19 total. So if I call, or some sequence on A, I print, and I return this. I get 4. So I got just the single value of 4 back. So returning n sequence B, it's going to be 4 plus n would be 1. Um, ah, gosh. Then B is half. Okay, so 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus then B is half the size of A, then just repeats process till B is. Hey Jeremy, thanks so much for coming in. It's good to hear from you again. So our function A gets called, A2 gets called, B right here, B now is at 1. So we return B0. But B0 is just going to be 0 because I'm making it 0, right? Yeah, this is DSA in Python. Data structures and algorithms in Python. We're on end of chapter 4 here. So I'm confused on our recursion trace here, right? So we start with some A4, assay length 4. A is length 4, right? This creates a new sequence B with a length of 2 now. Return No, I appreciate the help. No, you guys are doing great and like hinting me. I appreciate the hints and everything. To be honest, I'm struggling like pretty hard. Like I said in yesterday and the day before that, like recursion is really stumping me, and I need to practice this more and more. And so like, no, I really I appreciate the help. You guys helped me a lot. Um, so the thing I'm confused on though is we're making a new list of B, right? And we're calling some sequence of B. Why did I get an error here? Index out of range. So let's just go N. Or do I just need to multiply? No, I can't go -1. Let's try that. 4 still. Um, have you already covered Master's theorem in that book? No, not yet. I don't think so. Simple problems I understand, but like that English ruler, there's a lot going on. I mean, also maybe you already did this, but if you were me, I'd stop looking at code and just try to solve the problem by hand. For you, sample input A, understanding intuitively what's happening. Okay, so let's just stop looking at code and let's go back to the whiteboard here. So, right, we're taking in sequence A. Right, so A is equal to what we have above. 5, 3, 7, 4. Right? The sum of sequence A is 5 plus 3 is 8, plus 7 is 15, plus 4 is 19. Right? So we're looking for an answer of 19. Um, so we need to determine, um, she creates a new sequence B of half the size of A. So if we call the function of 4, right? Of n equals 4, right? We create at this call, we are going to create a new otherwise she replaces A with B and repeats the process. So B does not equal 1, so he creates a B at this point is equal to 2, right? Okay, so we're not B does not 1 here, so we're going to call another function call for n equal to 2 now, right? Well, in this function call, we create a B that has a length of 1. Okay? Well, we met our match here. So she sets B at index. So we need to set B at index 0 to so at this point we need to set B index 0 equal to A index 2 times 0. Okay? But then we need to set to, so at this case, our plus so in this case we have 0 plus um, plus what variable? We need to go up 1 every time. So right, so our I is 0 in this case. So what variable is going to increase every single time? N is going down by 2. Our B variable plus the length of B minus 1. Like that? I mean, because B at this point is equal to 1. We don't want to add 1 here, we want to add 0. So we need to add length of B minus 1. And in this case, we want to add 1, which would be length of B minus 1, right? Like that? What do you guys think? Am I crazy? That looks a little crazy. I don't know. Um, okay, we got some chats. Where did you learn or learning? I'm reading data structures and algorithms in Python right now. Quickly, while I wait for some more messages, for those that don't know or are new here, my name is Michael. Welcome so much thank you so much for joining me this evening. I stream almost every single day, live learning of Python. I'm really dedicated to learning programming and teaching myself. I graduated from college back in 2021 with a bachelor's of science in human biology and a minor in chemistry. I really focused on the cellular aspects and physiological aspects of human biology on like a microscopic level. Um, I was really interested in just like life in general, biology and life. Also, kind of in plants too. I took some more plant courses as well. Um, and I quickly got a job out of school after 2021. When I graduated as a formulation chemist for a biotech company, and I've been working there for 3 years. I'm currently a scientist too, as a formulation chemist, and I'm enjoying that. But I also wanted to further expand my knowledge and my area of expertise and my skills. And so I started to learn programming. So I started with Harvard CS50P online, offered online through EDX. Um, I took that course completely free. I did not pay for the certificate or anything. I took it completely free. I did it over the course of this past summer, 2024. I completed it at the end of the summer, and that's when I kind of got hooked. I really started to enjoy making projects, learning more, in depth, challenging myself to learn more challenging topics. Um, and so for the past 3 months, since about September, I've really been dedicating myself to live streaming my learning on this channel. And so I think we've grown really rapidly over the past 3 months in just our raw learning and abilities to program through obviously doing learning in at the beginning of our streams in formal textbooks and various online resources. For those that don't know, I've already read. Let me break out my little library here. I've already read all of Python Crash Course live on the channel, part one, which was the fundamentals of Python learning. We will eventually get into the Fluent Python as well as Python machine learning shortly after we complete the data structures and algorithms, which because I'm really enjoying learning this. And yeah, so that's my background in programming. I've recently completed a task tracker project completely written live on stream here. It uses object-oriented programming, saving and writing files, um, reading and writing files, sorry, custom imported modules using third-party libraries as Cauce. So it's a really cool program. Go ahead and check that out and on my GitHub and take it and use it if you want it. It's really cool and maybe try to mess around with it. But right now we're working on a small business manager on the back half of my live streams and on the weekends especially where we are creating a new project live from scratch, which is our own idea, own code, completely live on stream here. So we're really trying to make a number on our learning and improve. Okay, let's get caught up on the chat. Um, Next Sec 01, thanks so much for coming in. I appreciate you coming in and stopping by. Hello. That's a good course. I did that too. Did you get the certificate from the Harvard course? I got the free certificate. I don't. I highly advise that you don't pay for the certificate. It doesn't bring you any sort of actual backing, in my opinion, in sort of like job credibility. It's often seen as a very beginner and entry level course, and often I don't think a lot of tech companies are looking for a little bit more skills, unfortunately, than that. So from at least what I've heard, obviously in the biotech. I'm not a programmer. I'm trying to learn programming. That's the whole point of this channel. Is I'm teaching myself and live streaming it to you guys to also follow along and hopefully maybe motivate or assist you guys in your pursuits and learning independently as well. From a beginner's perspective is what I wanted to bring to the table. I felt like a lot of other streamers and video creators were really advanced, and oftentimes it was hard to keep up with what they were doing. It made me want to give up, but I wanted to. I felt that there wasn't actually a beginner that was willing to show himself, putting himself out there just from scratch, like really just like bare and say, I don't know anything. Let me take it all in, and yeah, and just trial and error. So that's basically what this is, and we've created a little community. So I thank you guys so much for joining me on the stream so far. I stream every day, at least I try to, 7:30 to 7 PST to about maybe 9:30, 10, sometimes 11 when we get really cooking into these problems. But yeah, I appreciate you guys being here. Yeah, so along the CS50, yeah, so I highly advise you don't get the certificate, just pay for it. You will get a certificate, a free version, but it teaches you all the same concepts. It teaches you everything is the same except for just a valid certificate versus a free certificate when honestly those don't really have any difference either. Hey Snake, thanks so much for coming in. I appreciate you coming in. I like that name, Snake with the four. That's cool. Jace, I'm a software engineer, but if I was interested in getting into cellular biology a little bit, the way you're getting into computer science, what would you recommend I start? Um, I would honestly, it's kind of crazy, but you could model a similar point of view of I would pick up a biology textbook. Biology is just really dense in terms of you'll find obviously computer science is really dense, but biology you just keep getting smaller and smaller and more microscopic and more microscopic and more microscopic, and at each of those points you just have more and more things that are there like that we have discovered through just like various testing, right? You have to memorize like proteins and their travels and their pathways. You have to memorize and know like certain types of interactions with like organics molecules, and that's just very broad in general, but um, it's just like once you learn one subsystem, you dive even further down, like into the muscular system. You have like these the striations, and then each one of those, and the filaments, and then it gets more microscopic, and it's really it compounds really fast. I guess similar to software engineering. So uh, I think you guys are so kind. Yo, I heard you mention taking the machine learning route, Michael, and I immediately stopped studying to came back. That's awesome. Where you also in machine learning? Oh yeah, it was just we have a book here that I'll eventually get to. I picked up this book from Facebook Marketplace for real cheap, Python machine learning. So we'll eventually get into this when we get some more algorithm practice, and yeah, it's gonna be great. Okay, so back to our function here. So we need to is this what we need to do? We set b at index 0 to a at index 2 times 0, right? And plus, right? We need to add 1 each time we go up. So if that's the case, if that's the case, the only number I can see in our function that is decreasing by 1 every time is our b value. Well, b is just the length of our new recursion string or data frame or whatever. So can we just reduce this by 1 for this current iteration? I mean, let's maybe try it. Okay, so we want to return b. And we want to return oh, I see I'm lost again. Like she creates half of b and sets a half of b size and sets b at index I to 2 times I. What do so I return, I recall the function, and I need to return it with the value. I need to add the 4 to the 7. So I need to add it to oh. Oh boy. So what I'm not getting though is how are we setting b like what is we return. So this is gonna break our. We're gonna create a thing of 2. Okay, so this is 5 and 3, 7 and 4. Right? This sets b equal to half of it. Ugh, I don't know, dude. Like I really I don't want to go to the almighty orb yet, but it's looking like I might have to. If b has a size 1, then she outputs b0. Otherwise, she replaces a with b and repeats the process. So we replace A with B. So what I don't get is if we're reducing by half every time, plus A at index n, what would that give me? An index error out of range. Um, so ah, let's say this. Let's take this guy. Let's go. I am having trouble understanding this. Um, I get that I am doing a recursion down until um yeah, that looks crazy. I don't know. That looks nuts, Chase. There's no way I would have gotten all that. That just I don't know, that looks a lot harder than anything we've seen so far. So let me go up to this example here. We had a power example where we computed a partial power. No, not there. So let's go like this. Let's take the problem down until my B. Okay, hold on. Let's get rid of this. Let's go down to our problems. Ugh. Let's take this guy. Go into the almighty orb. I am having trouble solving this problem. Don't show me code. Ask prompt me for to gauge my understanding. Okay. Oop. Let's break this problem into smaller pieces and analyze it step by step. I'll guide you with questions to understand the algorithm better and assess where you're stuck. Sequence halving size. Size halving. Isabel creates a new sequence B that is half the size of A. What happens with A after each step? How many steps will it take for A to reduce from n to a single value? It'll take, so 4, it'll take in each step, Isabel calculates B at index I, okay, for all I. How many additions are performed in a single step? Given that the size A is n at the start, right? You got to do n iterations, right? Because you have to sum up every value in n. Total work across all steps. After the first step, the size A is reduced by half, so the work number of additions decreases in subsequent steps. Can you express the total number of additions as a sum of over all steps? So this is what I got so far. This is what I have so far. Good start. It seems like you started thinking about the recursive structure of the problem. Let's clarify the process and improve your understanding. Your current function demonstrates that you're aware of how the algorithm shrinks the array and recursively towards the base case. Here are some issues to address. What's missing in you've created a B, but you haven't calculated its values based on this. You're calling some sequence B, but this doesn't reflect the logic of replacing A with B. Okay. Breaking down the structure and steps. Let's see, answer the questions from before in your relation to your code. How many steps does it take for A to shrink to size 1? N minus 1, right? It takes n minus 1 steps to shrink down. So we need to call, okay, what is happening in each step? In each step, you're performing n divided by 2 additions. N divided by 2 additions. Okay, so n minus 1 over 2. The number of think about the total work. The number of additions in step 1 is proportional to n divided by 2, and step 2 is n divided by 4, and so on until k, where the size is A, is equal to 1. Can you write the total number of additions as a sum over these steps? N over 2 to the power of n. Not quite. Let's revisit the question carefully. The goal is to determine how many times you repeatedly have n, a power of 2, until it becomes... Repeatedly have n until it becomes 1. Step 1, n divided by 2, divided by 2, divided by 2. Yeah, so it's a log 2. Okay. Now that we know that it takes log 2, let's think about the steps work's done. What's the total work additions across all steps? What does you mean work? Total work. Ugh, that's crap. All right. We got a lot of chats here. Holy crap. Finally call. Oh, okay. So you're not making any sense. Stop talking about work. I don't like talking about work. Okay, so step count. The goal is to figure out how many steps the process takes and what the running time of the algorithm is. So steps is n minus 1. Close, but not quite. Let's clarify why the steps is not n minus 1. The number of steps is determined by how many times you have to have n. So to get to have the 1 in this, you'd have to have this once, twice. So you have to have it twice if you have 4. if you had a 16, 8, 4, 2, 1, 4. Not quite. So you'd have to. Two to the power of 16. 2 to the power of 4 is equal to 16. So if n is equal to 16, you take the log base 2 of it. You take the log base 2 of n, so you take the log of n. Or, so if this is n, 2 to the power of 4 is equal to n. So you, come on, load. Okay, the number of steps Isabelle algorithm takes log n, or the initial size of the sequence. Why is it log n? Well, yeah, we predicted this before. Like, we knew that it was having just based off of this, like, thing. So, like, why did I make this so complicated? Like, does this clarify things? Okay, now where do we go from here? So if we're, like, how does this help us? Oh, I want to write the algorithm. Okay, start with the sequence A. Input a sequence A of size n where n is a power of 2. While the sequence has more than one element, create a new sequence B where each element is the sum of consecutive pairs of A. While the sequence has more than one element, else we need to create a new sequence of B it's more than one element. So you have this sequence, 1 all the way to 8. So you sum what kind of loop will you use? So you do have to loop. Okay, so that's what the problem is. As I was trying not to loop, like I didn't get that we had to loop. So we need to say, walk through the algorithm. A is this. Initial sequence is A. Pair sums. B is going to, we want to return B index I is equal to the sum of the sequence B plus, so if n is 1 and minus 1, a index n minus 1 plus that. So this equal to something like this. So if length of b is equal to 1, we want to return, so we will return pair sums. Oh. Um, okay, let's get caught up here. What camera are you using? I'm just using my MacBook camera, MacBook Pro camera. What is the syntax in line 12 creates honestly tough for me who works in C? Okay, so at this case, right, B, I don't know what I'm doing here. Like, honestly, like, this is rough. Like, what the heck is going on? Index error. Ugh. So this will be B at 0. So what if we say just N, B at 0 equals... So B, N is 1. What happens, what do we get here? Index error. This is so annoying. Michael, I think you're misunderstanding that for each recursion function call, you loop until n is floor 2 and set each value of b. Am I just misunderstanding the problem? Like, is it just a miscommunication here? Oh my goodness. So, for each recursive function call, you loop until n divided by 2. You loop until n divided by 2. And set each value of b. So what's happening here? We have our initial function list A. B is created, which takes a half of the values, placeholders, and in index B0, we're doing index I, or index A0 plus index... Okay. This is tricky. Okay, so we take the length of A, we determine that it's that it's n, right? Then we say um, while n is greater than 1, we're going to, while n is greater than 1, no, I don't know. Hey Eric, thanks so much for coming in. And Gustav, thanks so much for stopping in. Appreciate you guys stopping in. Um, okay, what kind of loop will you use? How will you calculate the sum to form B? How do you stop the loop? So I first take length n equal length A, right? Yes, that's a good start. Setting n equal length A. You're establishing the size of the input sequence, which is essentially for controlling your algorithm. Now let's proceed from steps here. Check if n is greater than 1. Since you only stop if the sequence has a size 1, you'll need a loop that runs while n is greater than 1. What kind of loop will you use? A while loop works well for this structure because the size of A keeps shrinking. So while n is greater than 1, we want to inside the loop initialize a sequence. So we'll take our sequence here, put it inside our loop, and then for each index, for I in n, b of I range of n, for b of I is equal to a of index I plus a of index I plus 1. But this says 2I, so 2I plus 1. Two I plus 1. How will you loop over the indices? Um, okay. I don't know how I'm doing. um, okay. Um, you're giving too much info. You are. We give the wrong your. um, so I have this now. Right on track, just a couple of adjustments. Range I, since n divided by 2 is a floating point, you should use floor division. Instead. Okay. Okay. This what I got so far. Very close. Okay, stop showing me code. I have to tell it like 10 times. Like, can they please like update this stupid AI to like remember a little bit of like one sentence in my work session here? Uh, okay, once the loop finishes when n equals 1, you'll have a single element A, which is the final result. What will you do with what will you do after the loop finishes to return the result? Um, After the loop finishes n equals 1, you'll have the final result of the first element of the sequence A. You need to return that element. To summarize, you initialize A and enter the while loop. Inside the loop, you keep halving the size of A, summing cumulative pairs until and updating A each time. The loop continues until n equals 1, which means A only has one element. Finally, return element A as the result. Return A? What? All right. Honestly, if I fail my database finals tomorrow, it's on you, Michael, bro. Tough. Okay. Return A? You're close with a small issue. You're still using range, which will miss the last pair. It should be just to cover all pairs. Okay. So the key steps to focus on are after filling B, assign B back to A and have N. So you don't need this. I don't know. This is crap. I don't know. I have no idea. Oh gosh, I have no idea. This is just so frustrating. Like they throw you one of these stupid problems like without giving you. Oh, it's kind of annoying. We got this. Okay, so also B is equal to A, N is equal to N divided by 2. Okay, come on. After you leave where you calculate B, you set A equal to B to replace. So you set B A equal to B, return. Keyboard interrupt. I'm not interrupting it. Oh my gosh. I got no idea. Like, this is just so dumb. I'm just like defeated. Should be inside the while loop. So we need to set A equal to B here. Case, no code. Gosh, it's just terrible. Like, I have to tell it a million times. Start with the sequence A, get the length of A, which is n. While n is greater than 1, create a new sequence B that will hold the sum of all the sequence pairs. Okay, got you. 2 times I. Do I need to int I? Why can't I do this? All right. Hey, Garvit, I thanks you for coming in. I appreciate you. I would consider returning if length A is equal to unreturn. Return length A. We can't even do that. I get a list index error. My A has an even number of elements. Okay. N equals length A equals 1 B divided by 2 for range A. Turn A. Oh, they have it in the 4. Gosh. So if I just did that. Oh my gosh. Screw this problem. Like, to be honest, guys, like, I've never done this before. I've never done a while loop with a variable, like, ever before. And this is the first time in the book that they've had us do this too. So, like, they just threw this at us, like, without, I don't know. I'm kind of triggered, to be honest, because all these other ones were like pretty, decently okay, and then they threw this while one that has a while loop in it when we never saw a while loop example. I mean, we saw here with the binary search, but this was like this was a high low call. This wasn't like a using a length variable. Ugh, yeah. So I had never seen this like done this before. So yeah, this is terrible. Fail, fail, fail. So defeated. I'm just trying to be transparent with you guys. It's not all rainbows and butterflies, and it's like this is kind of the reality of it sometimes. And you know, I would it would be lying for me to say like, oh my gosh, like this was really easy. I did all this in one go, right? It's just not true. Um, Incognito hack. Sorry, I've been missing messages. I've been focused here. Sorry, I'm so sorry. Thanks so much for coming in. I appreciate you. Lewis ECV, thank you for coming in. Yeah, this exercise about recursion. We were struggling through. Yeah, so I appreciate you guys sticking with me here on the stream. Please consider, following along, subbing to the channel. We've been growing really rapidly. It really, just helps motivate me to also just keep going. Just, obviously I'm going to keep going no matter what, but just having that extra boost just obviously helps. Just, I appreciate you guys joining me and being here and taking your time. That's what really matters, though, is you guys' time being here with me. So thank you so much. Um, Honestly, if you delete the while loop and move your base case to the top, you're getting super close. Yeah, like when we first did this, like, so if it so key takeaways here, guys, is if it gives you some sort of mathematical problem like this, from the looks of it, is we're going to have to literally have this written in our code. Like, if they give you some sort of like setting a boundary of like some sort, you we had to have written this in somewhere, and as you can see, it was here, and we were given a range value here. So okay, so that should be just an immediate indicator. If we for the future, right? We need to learn from these mistakes, right? In the future, if we are dealing with indexes, if we are given a mathematical operation to perform, and that mathematical operation performs over a range of indices, we most likely need to loop over a range of indices and perform that mathematical operation provided, right? Just that just seems self-explanatory. I don't know why I didn't think of that in the moment, but in hindsight, you know, is what it is. Yeah, guys, the channel is so close to 500 subs. So close to 500. It would be such a huge milestone to hit, and we've been growing so rapidly. It's just unbelievable. I tell my girlfriend, like, I'm like, I'm getting like 10 more. This is crazy. Like, people are talking to me in the Discord. Like, you guys don't realize how like cool this is to me. So, what would be the running time of this algorithm? Like, that's what we need to solve, right? And I saw that you guys in the comments were debating um, this running time. So, right off the bat, we know that we're performing a logarithmic operation just by having our n values every single time and creating a list. But what we're doing is we're also accessing every single value within the A list, right? So we are doing that. So my initial instinct from when I first saw this was we're going to have a log n, but now that I see this that we're accessing n values per log n, that just kind of indicates and leads me to believe that this would be a n log n function. O n log n. What do we feel about that? How do we feel about that? Does anybody have a better reasoning than what I just provided? I'm sure you guys do. Please give me a better reasoning that would help me understand this. So we're performing a reductive operation by 2 over our values of n every single time. But we are then, accessing every value technically within our A here. We are accessing every value in our A and doing some sort of mathematical operation on them. Now this is constant, each one of these, but together are we going, technically accessing each one in the range. All right, so let's get caught up on the chat. Hey, Coding Mountain Man, I appreciate you coming in. Sorry I haven't gotten to your chats. I appreciate you coming in. You've been chatting a lot. Thank you for participating. You don't need a while loop to solve this problem, just a single for loop. So if I got rid of the while loop, I moved this back, and I took this, I put it up top here, got rid of this, and said else do this, would this basically I lost my sequence A1. Shoot. 3, 6, 4, 1. So this would be 9, 13, 14. None. So this gives me none. Yeah, I graduated college back in 2021. I have a degree in human biology and a minor in chemistry. Yeah, Jeremy, many, many fails to come. All good. Appreciate the support. Thank you. Length A is equal to 1. It's not the right base case. When you say if but you're dangerous. Don't set A equal to B, but make sure the function ends with some sequence B. Okay, so like kind of how I was doing it before. So we're not going to set A equal to B. We're going to call recursively if this, else do this. And then we need to call some sequence on B. What happens over here? Get none again. So we know that this, if length A is equal to 1, return A. Meaning that we have one value, we return it, else we're going to do this. Probably need to keep this guy, I would bet you, above. Thank you for the sub. I appreciate you. Make sure it ends with sequence B. So what do we do with I'm really not sure what's going on with this. Like what is going on with our N here? I'm looking at different tech unis right now for online debating bachelor's at ECS with the AI and machine learning that's focus or cybersecurity. Hard choices to decide upcoming career-wise. Don't put too much pressure on yourself. You know, you got life ahead of you to learn. Don't try to make it seem like you got to learn everything right now, or else you're gonna miss the boat. No, no, no. It's definitely that's a societal pressure put on by industries to get you to pay them and to not miss out on FOMO on things. But take things at your own pace, learn, solidify the knowledge, just like we're doing here, and we'll be okay, right? You and me together. So at the start, we're going to create m equals n divided by 2 and say so this is times m, this is times m, gets rid of that, that returns none again. M is equal to 0, return A. A0 plus A1. out of range, we just return A1, A0, none. Why are we getting none? Oh, m equals to 1. Sorry. That gave us a none back as well. So n is our length A. M is a reduction every time. Is our step. So if our step is now 1, meaning that we reach our base case, we return A, none. Else we create a new B sequence times n for range up to M, sequence B. Don't need that else. A0 plus A1. So we wouldn't need all this. So could I delete all of this? Would I not need all of this? Whoever just subbed, thanks so much for subbing. Appreciate you. Got the balloons. Yeah, let's see if I can get the fireworks to come up. Boom! We'll be the Costco guys. Boom! I don't know why I'm so obsessed with those guys. Okay. So this returns us a none still. So what is wrong with our function here still? Yeah, I'm getting a none returned back here. Let's see what the almighty orb has to say about this guy. The sum sequence function appears to recursively sum elements of list A in pairs. However, there's a missing return value. Oh, that would be the problem. Return sum sequence B. Ah. Okay, so we didn't need a while loop then. We could have, okay. So this was the approach that we should have done the whole time. We were so close then. We were close. Ah, we were so close. That's what she said. Dang it. I'm kind of pissed now because like we were right there. We were saying if A is equal to length A, we're saying is equal to 1. Oh, we were right there. Dang it. Ah. Okay, that's good to know. All right, so let me ask you guys this. Should we try another recursive example? Should we do one of the creative problems? Now, I only usually do the reinforcement problems. Do you guys want to see another reinforcement problem? Or reinforcement problem, move on to chapter 5, which is about array-based sequences. Recursion problem, chapter 5, or Python project, small business manager. What do you guys want to work on? We got 20 people in here. Thanks so much for spending some time with me here and learning. I appreciate all of you guys, each and every one of you guys supporting me. Thank you. And supporting yourselves as well. What do you guys want to see? Chapter 5, recursion practice problems or live coding project. Another problem. I'm here for Max Payne. Chase says, seems like you should take a break. Jeremy says, another problem. Max Payne. You guys are just like, it must be one. We must have a toxic relationship. You guys enjoy me struggling through these. I feel like I'm not that great at these recursions yet, and I don't know. Describe a recursion. I'm going to compute the integer part of a base 2 logarithm of n using only addition and integer division. Okay, so I'm going to really, I think what I want to do is I'm going to try just a few more practice problems. I'm going to try to do 4.10, right? I'm going to try to do 4.10 here. I think this one is one that we can do to give us some confidence here. Now, if we can't solve it, then we might as well, I don't know, keep trying. We're going to keep trying, right? Positive thoughts here. Also, the idea behind why I said delete the else was because if the if statements get picked up, the function returns anyways. You add it back, the else wouldn't work though. Would still work though. Yeah, I got you. Thank you for that. Okay, so we want to describe a recursive algorithm to compute the integer part of a base 2 log of n using only addition and integer division. Okay, so this is going to be similar to our previous one as well, I think, right? So we want to define log function, which would take in the integer part of the base 2 logarithm of n, a value of n. So we would take in a value of n and we want to compute the integer part, which is the answer, which in the case of logarithms, right, is log base 2 4 is equal to 2 is 2, right? Yeah. So it's 2 to the power of the answer is equal to our n value, right? So just really quickly, 2 to the power of some value x is equal to n. Okay, we want to solve for x, right? Okay, cool. How are we going to do this? So compute the integer division part. Compute the integer part of the base 2 logarithm of n using addition and integer division. So we need to set up a base case. What would our base case be? That n is at 1 right? So we need to log n every single time until we get down to our base case where n is equal to 1. But m is equal to 1, right? And then we'll say m is equal to n divided by 2. Similar to our last problem, right? We are computing the floor at each recursion. Sorry, we're computing the step. The m is counting that current step. So if n becomes 1, meaning that we cannot go any further, this is our last step in our recursion, then we need to return at this point some value, okay? else, what do we need to do? We need to at this current recursion, we will call log of I'm figuring this out the same time as you, but I assume the key idea is log n equals log n divided by 2 plus 1. Return So what do we need to do to n? We need to return the floor. So what is the value? The value is the amount of steps that this makes, right? So the count of total m's. So integer part of a base 2 logarithm. So, right, 2 to the power of what gives us n? Well, n has to be... So if n is equal to 1, meaning that in this case we are using floor division on our starting value to give us our current step. Okay, that's the step 1 we've made. We have that step. If we're at our last step, we return some value here. We need to return not m, but we need to reduce m down by 1. So we would obviously have to call log again of m here, right? Because that's the iteration that we're making down. We return this. Return we need to count m, right? We need a total amount of steps that it took to reach our base case, which is our answer. So we need to return what do we need to return to our last statement here? James Peralta, yeah, we're working on recursion right now, so really struggling through it. I'm trying to teach myself using data structures and algorithms in Python, chapter 4. We just struggled really hard through 4.8, and we're doing another practice problem of 4.10 here. So you just have to say plus 1 here. And you return 0 to get the count. And you add 1 to m every time. Similar to what Chase was saying. So let's do log of 4. Right? That gives us 0. Oh, not inside the call, after the call. 1. So log of 4 should be 2. So we need to return 1, right? That'll give us 2. So, and now let's try log of 6 of, what does 16 give us? 4. Oh yeah, that's it. Log of m plus 1. We need to return 1, not 0. Hey, is it Callian? I really appreciate you coming in and saying hello. Thank you so much. How are you doing today? Are the problems becoming easier to understand? In all honesty, it's, I mean, I'm more familiar with maybe the structure of a recursion in general, but I still have struggles, deciding what variables to establish, where to use them, and you know, what to actually call back. And so I do struggle with like identifying the variables out of the problem, but I'm getting more familiar with the actual structure. If, else, returns, like we have to have returns in each with a base case, and then we also have to reduce our input by some sort of factor each time. And so this one we're reducing by a half each time, so we're having a logarithmic function here. Yeah, you return 1 if m is equal to n divided by 2, but if you don't define an m, you just check n is equal to 1 and return 0. Oh, so if you don't define m here, you just call if n is equal to, if n divided by 2 is equal to 0. Is equal to 1, return. But if you don't define an m, you check if n is equal to 1 and return 0. Like this, and then do log of n. Maximum recursion depths met. Just on the return line. Doing great. Happy to join this platform. We'll continue to join with you further. Awesome. That sounds great. Yeah, this is a great place for, programmers of all sorts of knowledge. Beginner, I'm trying to just remove that competitive pressure that's kind of placed on CS right now, with job hunting and money and all that kind of grab, and just create more of an environment just for raw learning and just pure trial and error, and the real, what really matters here, right? The material. Return. Oh, so we need to return 0 here, and then here return log and divided by 2. We had to keep it somewhere, right? Exactly. There. Boom. Cool. Yeah, so we if we removed it from a case up here to establish an m, well, we had to put it within our actual recursion call here, right? Because we were calling log m here, which was n floor 2. Cool. Okay, this one was a little bit better. We got this one in what, 15 minutes, not an hour and a half? Oh my god. It's a miracle. Oh. All right. Cool. This was the answer for this one. So obviously this one would just be a log n time, right? Sweet. All right, that's cool. I'm gonna create another folder in here and say extra practice. Cool. Yeah, the same way before, but now there's no m equals n divided floor 2. Exactly. We had to keep that operation, but we instead of a variable here, we actually put the operation. And we're doing plus 1, right? Because return log plus 1. Because you're starting off on this 0. Not often can you define the runtime of your algorithm in terms of the algorithm you just created. Yeah, we created a log n algorithm, so it is log n, right? So I'm having a little trouble. Why are we adding 1 here? We're going to return plus 1. So 0 gets returned. So then we get 1. And then we return into the previous statement write out the powers of 2. So we have 2 power 1 is 2, 2 power of 2 is 4, 2 to the power of 3, 2, 4, 2 times 2 is 4, 2 times 2 is 8, 2 to the power of 4 times 2, 8 times 2 is 16. Or sorry, 1, 2, 4, 8, 16. 2 to the 0, 1. Zero, 1, 2, 3, 4. Log 16 equals log 8 plus 1. So why are we adding 1 at the end? In the recursive implementation of log n, the idea is to compute the logarithm of n to the base 2, right? The base case is n equals 1, which is the point where the logarithm is 0, to the power of 0 equals 1. The recursion works by dividing n by 2 at each step, which essentially shifts the exponent by 1. The plus 1 is added to the result of the recursive call to account for the division by 2. Every time the function calls itself, it's as if you're moving one step closer to the base case in n equals 1. And the plus 1 keeps track of how many times you divided n by 2. Okay. For example, the first call is log 16 would be log 8 and adds 1. Adds 1 on for a total of 4. Okay, so we're returning 0 plus all of those added numbers. 1, 1, 1, 1. Okay. Recursively. Okay, just by the nature of the log. Interesting. Gotcha. Okay. Cool. Let's go ahead and dive into chapter 5 here. I feel like we have a lot of new people. We got 26 people watching the stream right now. Thank you guys so much for being here. It's not every day that, or it's not an easy task to, watch programming and set yourself to learn. But we're definitely we're moving along here. Okay, so this was my chapter 4 notes. I'm going to make a new dir here, a directory for chapter 5. If you guys want access to my notes and all these solutions and stuff that I'm making, um, it's all on my GitHub, right? So if you guys want to, access it for yourself, just go to my GitHub and it's all there. All right, see you, Chase. Thanks so much for your help. I appreciate you, and no worries. You were a great help this stream, and I look forward to reconnecting with you and tomorrow or in later streams. Thank you so much for stopping by today. Okay, so chapter 5, we need chapter 5 notes.md. Okay. Let's go. How did we set up our chapter 4 title? We did definitions up top, and then we set up into the actual body here. So let's just copy this over. I'll take these. I'll delete here. Chapter 5. Set this up. and then let's get into array-based sequences. Hopefully this one's a little bit better than recursion. I like arrays. I can wrap my head around arrays a little bit better than recursion. 5.1. Okay, Python's sequence types. All right, let's dive into the meat of this guy. So for those that don't know, on my streams here, I read these textbooks aloud, live audiobook style. So if you were at work, you can throw in the lives in the background and listen to the me reading if you want to, for extra studying, or that's kind of what I do sometimes. Just to read it, listen to it in the background, and get some more, practice with it and more just hours listening to it over and over again. Yeah, so just use this as whatever tool you would like to rewatch and study, but also follow along. This is Data Structures and Algorithms Chapter 5, Array-Based Sequences, DSA in Python. You can get access to this copy in my Discord linked below, where I have conglomerated all of my study resources, and you can access these notes on my GitHub. All right. In this chapter, we explore Python's sequence classes, namely the built-in list, tuple, and stir classes. This is a significant commonality between there is significant commonality between these classes. Most notably, each support indexing to access an individual element of a sequence using a syntax known as sequence index K, and each uses a low-level concept known as an array to represent the sequence. However, there are significant differences in these abstractions that these classes represent, and in the way that instances of these classes are represented internally by Python. Because these classes are used so widely in Python's programs, and because they will become building blocks upon which we will develop more complex data structures, it is imperative that we establish a clear understanding of both the public behavior and inner workings of these classes. Public behaviors. Okay, so we're going to define probably list. We're going to define tuple here, and we're going to define probably stir here, right? Just off the jump. Public behaviors. A proper understanding of the outward semantics for a class is a necessity for a good programmer. While the basic usage of lists, strings, and tuples may seem straightforward, there are several important subtleties regarding the behaviors as associated with these classes, such as what it means to make a copy of a sequence or take a slice of a sequence. Having a misunderstanding of a behavior can easily lead to inadvertent bugs in a program. Therefore, we establish an accurate mental model for each of these classes. These images will help when exploring more advanced usage, such as representing a multidimensional data set as a list of lists. Okay, implementation details. A focus on the internal implementations of these classes seems to go against our stated principles of object-oriented programming. In section 2.1.2, we emphasize the principles of encapsulation, noting that the users of a class need not know what the internal details of the implementation. While it is true that one only needs to understand the syntax and semantics of a class's public interface in order to be able to write legal and correct code that uses instances of the class. The efficiency of a program depends greatly on the efficiency of the components upon which it relies. Asymptotic and experimental analysis. In describing the efficiency of various operations in Python sequence classes, we rely on the formal asymptotic analysis notations established in Chapter 3. We will also perform experimental analyses of the primary operations to provide empirical evidence that is consistent with the more theoretical asymptotic analysis. Okay, so basically we're going to use big O notation, asymptotic analysis from Chapter 3 to carry forward into arrays here. So kind of a lot of jargon here, but it just says, right, we have this principle of encapsulation, noting that the user of a class need not to know what the internal details of the implementation. They only need to know understanding the syntax of the public that they can access, right? And because of this, certain functions have underlying time complexities that we need to account for. So we need to know what those functions that are like built in have if we decide to use them. Okay, low level arrays, 5.2. Let's go like this. I'll take these. Whatever, I'll have to come back. There wasn't much notes we could have taken there, or could have taken. Okay. Low level arrays. All right. Get caught up in chat real quick. Jeremy, do you understand these problems? I have a CS degree, so I'm familiar. How often is data structures used in your job? Like stuff like this. How do you stay consistent? Honestly, you guys really help me stay consistent. The stream and the support I get on the daily here is just overwhelming, and you guys don't really. It's really hard to explain and put into words the sheer amount of positive feelings I get just from you guys being here and supporting me and interacting with me in the Discord, and it just really helps to just drive forward. Ultimately, it's you guys for sure. Okay, low level arrays. To accurately describe the way in which Python represents the sequence types, we must first discuss aspects of the low-level computer architecture. The primary memory of a computer is composed of bits of information, and those bits are typically grouped into smaller units that depend upon the precise system architecture, such as a typical unit. Such a typical unit is a byte, which is equivalent to 8 bits. Okay, so we have definition up here. We have a byte, and we have a bit, right? So a bit, primary memory of a computer, is composed of bits of information. These bits are typically grouped into larger units. The primary way a computer stores information in bits, right? Ones and zeros. A byte, let's make this one go down below the bit. A byte is a collection of bits. 1 byte equals 8 bits. I'm working on a master's right now, and at that level, algos and data structures, like you were seeing, are used all the time and are the difference between programs running or timing out. I have wrote programs that never finish, and when optimized can return an answer in under a second. Wow. Awesome. Cool. A computer system will have a huge number of bytes of memory. And to keep track of what information is stored in a byte, the computer uses an abstraction known as a memory address. Okay. We have a memory address, right? A computer system will have a huge number of bytes of memory, and to keep track of what information is stored in the byte, the computer uses an abstraction known as a memory address. In effect, each byte of memory is associated with a unique number that serves as its address. More formally, the binary representation of the number serves as the address. In this way, the computer system can refer to the data in byte hashtag 2150 versus byte data in byte 2157. For example, memory addresses are typically coordinated with the physical layout of the memory system and so often portray the number in sequential fashion. Figure 5.1 provides such a diagram with the designated memory address for each byte. Byte 2150. So byte 2150 has 8 bits inside of it. So there's 8 bits that comprise 2150. There's 8 bits. Each one of these blocks is 8 bits. So a memory address define memory address in relation to bits and bytes. A memory address is a unique identifier for a location in a computer's memory where data is stored in terms of bits and bytes. A primary way computer. The smallest unit of data. I like this definition for bits. We'll take this guy from here and paste it here. I like this, a group of 8 bits, which is often a single character of data. I'll take this definition for the byte. I like that one. And then memory address is going to be a unique identifier for a location in a computer's memory where data is stored in terms of bits and bytes. Okay. A unique address, right? Cool. If you guys are enjoying the stream this evening, feel free to throw it a thumbs up so maybe some other people could also get the stream in their feeds, and we could reach all the potential programmers that would find this information useful. Just to continue to grow our community and all build off one another would be great. Okay. Despite the sequential nature of the numbering system, computer hardware is designed in theory so that any byte of the main memory can be efficiently accessed based upon its memory address. In this sense, we say that a computer's main memory performs as random access memory. Alright, that's where we get RAM from. RAM. Random access memory. That is, it's just as easy to retrieve a byte at this address as it is to retrieve byte at this address. In practice, there are complicating factors, including the use of caches and external memory. We address some of those in chapter 15. Using the notation of asymptotic analysis, we say that any individual byte of memory can be sorted or retrieved in O of 1 time. So similar to our, I guess, like to accessing like a dictionary key, we can kind of view these memory addresses as dict keys, where we can access them by just calling this physical dict key if it exists. So we probably have a certain number of sequences of data, so we could probably say from 0 all the way to this is what's accessible, and then just go ahead and directly find this key bit or byte, I mean, right? Interesting. So low-level arrays, we'll make a note here and say that it's in constant. Let's say the individual byte of memory can be sorted or retrieved. Despite this equal. Okay, we'll say like this. Let's go like this. Bytes can be accessed by a computer through its random access memory, right? Bytes can be accessed through its RAM. So 3 is byte. By via its memory address, right? And we'll say byte hashtag 8675309. 10 May, thanks so much for coming in and saying hello. I appreciate you commenting. A good segue to this book would be the High Level Performance Python by O'Reilly. Speaking of that, I have the Fluent Python book. So we are going to be diving into this, and I think I know that this book, DSA in Python, is really long. It's 15 chapters, so it's going to take us some time to get through, unfortunately, just by the nature and the sheer amount of material in it. So I do want to start this Fluent Python sooner rather than later. We will have two books going on at the same time, but I think that these would go really hand in hand about like solidifying these more complex like Python loops and syntaxes needed for running these algorithms, right? Um, Janaya, I appreciate you coming in and saying hello. Thank you for stopping by. I really appreciate that. What time do you usually stream? Yeah, I stream after my 9 to 5 job. For those that are new, I have a bachelor's of science in human biology and a minor in chemistry. I graduated back in 2021 from a state college in the USA. I got a job right after college in 2021 at the beginning of 2022 as a formulation chemist for a biotech company where I've been for about 3 years now. Currently a mid-level scientist too, gunning for the next level soon. And anyways, I'm trying to teach myself code after my 9 to 5 and on weekends and documenting my progress from a raw beginner's point of view to you guys. And so if that's something that you're interested in or in a similar situation, I'm created this channel. I have my Discord linked below that I also created where I have compiled and um, conglomerated all of my study resources from the books I read as Fluent Python, DSA in Python, Python Crash Course. We also have a project showcase where I showcase various projects we're working on. I also do updates or stream announcements on there, all that kind of stuff. Tanmay, is Fluent Python similar to the high performance Python? What's kind of the difference with those? Okay, so then using the notation, we say individual byte of memory. An individual byte of memory can uh, be stored or accessed in O of 1 time, right? In general, a programming language keeps track of the association between an identifier and the memory address in which the associated value is stored. For example, the identifier x might be associated with one value stored in memory, while y is associated with another value stored in memory. In general, programming keeps track of association between identifier. Okay. A common programming task is to keep track of the sequence of a related objects. For example, we may want a video game to keep track of the top 10 scores for that game. Rather than use 10 different variables for this task, we would prefer to use a single name for the group and use an index number to refer to the highest scores in that group. A group of related variables can be stored one after another in a continuous portion of the computer's memory. We will denote such a representation as an array. Arrays. Here we go. You think DSA and you immediately start thinking arrays, right? Array. That's all you hear online. Here we go. Diving in. A group of related variables can be stored one after the other in a continuous portion of the computer's memory. A group of related variables stored in continuous fashion, stored continuously in the computer's memory. As a tangible example, a text string is stored as an ordered sequence of individual characters. In Python, each character is represented using the Unicode character set, and on most computing systems, Python internally represents each Unicode character with 16 bits, 2 bytes. Therefore, 16 character strings such as sample would be stored in 12 consecutive bytes of memory, such as diagrammed in figure 5.2. So each character using the Unicode character takes up 16 bits or 2 whole bytes itself. So as you can see, the character S is filling up byte 2146 and byte 2147 for an index of 0, right, in this array. Interesting. Okay, so let's go here and say arrays or we'll say text using the Unicode character system. Text characters using the Unicode character system take up 16 bits or 2 bytes of memory per character. So 1, 2, 3, 4, 5, 6. 6 times 2 is 12. Would be 12 bytes. Okay. So quote. So we'll say example is quote sample has 6 car, right? 6 characters times 2 bytes each equals 60 or 12 bytes total for the array sample in the system's memory. Right? The string array in the symbol array. All right. Jeremy says chapter 5 through 11 all look like data structures that shouldn't be so heavy on the brain. 11 through 15 is heavy, but some of the coolest CS concepts. Are you talking about the book that we're currently reading? Chapters 5 through 11 all look like data structures that shouldn't be heavy on the brain. Chapter 11 through 15 is heavy, but some of the coolest CS concepts. Okay, gotcha. Yeah, so 5 through 11 is so right now we're talking about arrays, data structures. Okay, gotcha. Zavek, thanks so much for coming. I appreciate you stopping in and saying hello and joining me. Funny how I get recommended this before my machine learning final. Awesome. Yeah, this would be a great little maybe beginner refresher for those beginning concepts. Yeah. Tomei says Fluent Python is all about the features Python has to offer and how things work in Python under the hood. High performance Python is for efficiency in Python and dealing with CPU bound problems. Maybe we'll have to pick up a copy of that one as well and maybe read them both. Might as well, right? Yeah, if that's something you guys are interested in, let me know and I'll pick up both of them and we'll do them both. Oh, awesome, Jeremy. Okay, cool. Well, I'm looking forward to learning these data structures then and getting more practice with them here. Okay. We describe this as an array of 6 characters, even though it represents 12 bytes of memory. We refer to each location within an array as a cell, and we'll use an integer index to describe its location within the array, with cells numbers starting with 0, 1, 2, and so on. For example, figure 5.2, the cell of the array with index 4 has contents L, and is stored in bytes 2154 and 2155 of memory. Each cell of an array must use the same number of bytes. This requirement is what allows an arbitrary cell of the array to be accessed in constant time based on its index. In particular, if one knows the memory address at which the array starts, 2146 for example, the number of bytes per element, so it starts here, 2146, the number of bytes per element, 2 for a Unicode character, right? 2 bytes per character, and a desired index within an array of the appropriate. So in particular, if one knows the memory address, the number of bytes, and a desired index within that array, and the appropriate memory address can be computed using the calculation start plus cell size times index. By this formula, the cell at index 0 begins precisely at the start of the array. The cell at index 1 begins precisely cell size bytes beyond the start of the array, and so on. As an example, cell 4, the L, begins at memory location 2146 plus 2 times 4, 2154. Okay, so if you want to access... Okay, so this is just telling us the start in terms of the actual memory location address plus the size of the cell. So each character has 2 bytes, and then you multiply it by its index. So this is just creating a starting position and then factoring through that start to find that index based on its cell size. So you're just skipping over cells based on the... Okay, got you. Okay, that's interesting. I wonder how... I'm gonna have to think about how I'll take notes on that. Of course, the arithmetic for calculating memory addresses within an array can be handled automatically. Therefore, a programmer can envision a more typical high-level abstraction of an array of characters as diagrammed in this. Okay, so it's just trying to set us up with to understand that arrays are similar to lists in a form, but we're taking into account systems of memory as we're placing in these objects, or because these are objects, stir objects in the memory itself on the computer. So we're not only creating lists in Python, but we are also creating arrays that are saved within these systems of memory. Okay, so if you have an array of tons of characters, right? Or you have a huge data set with lots of characters, well, I wonder how characters save with respect to integers, right? How do strings save with respect to integers? Are integers, do they take up less byte size? So you can have more integer processing power than in strings? That's interesting. I'm sure we're going to find out. Okay. Okay, 5.2.1, referential arrays. As another motivating example, assume that we want a medical information system to keep track of patients currently assigned to beds in a certain hospital. If we assume that the hospital has 200 beds, and conveniently that those beds are numbered from 0 to 199, we might consider using an array-based structure to maintain the names of the patients currently assigned to those beds. For example, in Python, we might use a list of names such as Renee, Joseph, Jeanette, Jonas, Helen, and Virginia, ... To represent such a list with an array, Python must adhere to the requirements that each cell of the array must use the same number of bytes. Yet the elements are strings, and strings naturally have different lengths. Python could attempt to reserve enough space for each cell to hold the maximum length string, not just currently stored strings, but any string that we would ever want to store, but that would be also wasteful. Okay, so what it's saying here is we are storing strings within the memory itself, but these strings have differing lengths. And we know that each character is composed of 2 bytes. So this would be 2, 4, 6, 8 total bytes, whereas this would be 2, 4, 6, 8, 10, 12 bytes, right? So how does Python, it's saying Python could in advance reserve a X number of bytes for a string and just always keep that available, and it'd be within a bound that any string could fit into, really, but that would be pretty wasteful, as it says, right? To hold a maximum length string, not just the currently stored string, but any string we might want to ever store. But that would be also wasteful. Instead, Python represents a list or a tuple instance using an internal storage mechanism of an array of object references. Instead, Python represents a list or tuple instance using an internal storage mechanism of an array of object references. At the lowest level, what is stored is a consecutive sequence of memory addresses at which the elements of the sequence reside. A high-level diagram of such a list is shown in Figure 5.4. Instead, Python represents a list or tuple instance using an internal storage mechanism of an array of object references. At the lowest level, what is stored is a consecutive sequence of memory addresses at which the elements of the sequence reside. Although the relative size of the elements may vary, the number of bits used to store the memory addresses of each element is fixed, 64 bits per address. In this way, Python can support constant time access to a list or tuple element based on its index. So is it assigned 64 bits? Traditionally, chars are 1 byte depending on the encoding. Like UTF-8, it can vary from 1 to 4 bytes. Okay, gotcha. So I want to take this, explain this to me. What if a char exceeds 64? Wait, explain this to me. In Python, when we talk about accessing an element in a list or tuple, we are referring to how the program in particular value finds a particular value based on its position or index in that list or tuple. Let's break down the concept. Memory address and fixed size. Memory addresses are locations. Each element in a list or tuple has a memory address, and the way elements are stored can vary in size. For example, an integer might take up to 4 bytes, while a string might take more. However, the number of bits used for each memory address is fixed. In most modern systems, this is typically 64 bits for a 64-bit operating system. This means the memory address itself is represented by 64 bits, regardless of the type of size of the element being pointed to. Constant time access. Constant time access means that the time it takes to retrieve an element from a list or tuple does not depend on the size of the list or tuple. This is what happens in O of 1 time, which is very efficient. Python can achieve constant time access because the fixed number of bits can be calculated. It can calculate the exact location of any element in the list or tuple using the index. Python stores values in memory, such as the way the integers have specific memory addresses. Address for the first element might be 10 with something like this. The address for the second element, 20, would be at a fixed distance from the address 10 because the integers are fixed size, 4 bytes. Although relative size, okay. In figure 5.4, we characterize a list of strings that are the names of patients in a hospital. It is more likely that a medical information system would manage more comprehensive information on each patient, perhaps represented as an instance of a patient class. From the perspective of the list implementation, the same principle applies. The list will simply keep a sequence of references to those objects. Note, as well, that a reference to the none object can be used in an element to the list to represent an empty bed in the hospital. In fact, that lists and tuples are referential structures and this is significant to the semantics of these classes. A single list instance may include multiple references to the same object as elements of the list. In fact, lists and tuples are referential structures and is significant to the semantics of these classes. A single list instance may include multiple references to the same object of elements of the list. And it is possible for a single object to be an element of 2 or more lists, as those lists simply store references back to that object as an element. When you compute a slice of the list, the result is a new list instance, but that new list has a reference to the same elements that are in the original list as portrayed. Okay, so this was a lot of jargon, but what this is saying is that the list, all it does is that it will house access to that object. So yeah, we can store, simple chars, and we can store strings and integers and floats in lists, right? But you have to think that these are actual data representatives that are accessed on the computer's memory. So we can store things like objects, and integers in themselves are kind of like there's int classes, right? So they kind of are objects in themselves, but we can also store custom objects in lists, just like we have been doing this whole time, right? And then if you create copies or aliases of lists, meaning that you can access a list by two different names, or you create a slice, which is a completely new generation of a list from a certain point to a certain point. Um, those objects are still the same. If they are objects, right? They're still the same objects that they were originally in the memory. They just can be accessed in two different arrays now, but they still have the same memory address to that object, I believe. Yeah, this is data structures and algorithms in Python. I appreciate you coming here. Say Jabir. Sorry if I pronounced that wrong. I am very white and very American. I uh, I apologize if I pronounced that. I butchered that name. Okay, cool. When elements of the list are immutable objects, as with integers instances in figure 5.5, so we have a figure here which has object 2, 3, 5, 7, 11, 13, 17, 19. We have a list of primes which house objects 2, 3, all these, but we also have a list of temps which houses 7, 3, and 11. 7, 11, 13. The result of the command temp equals prime. Okay, we take a slice. Okay, so temps is a slice from 3 to 6. Gotcha. When the elements of the list are immutable objects, as with the integer instances in figure 5.5, the fact that the two lists share elements is not that significant, as neither list can cause a change to the shared object. If, for example, the command temp index 2 equals 15, right? We would ask temp index 2 would give us equal, or executed from this confirmation. That does not change the existing integer object. It changes the reference in cell 2 of the temp list to reference a different object, right? So if we physically override our sliced list, right? Remember, guys, with Python syntax, when we create slices of lists, we are creating copies, right? It's not an alias, it is a copy of that list with reference to those objects. Now, if we go ahead and reassign that object to a new object, right? This can show that this list, we assign 15 here, and it is unique in this case. Does not change the existing integer object. It changes the reference in cell 2 on the temp list to reference a different object. The resulting configuration is shown in figure 5.6. The same, okay, so 5.6, oh yeah, that's what we just looked at. Okay. The same semantics is demonstrated when making a new list as a copy of an existing one. Wait, a slice isn't a new list? I thought a slice was a copy. Am I wrong? Is a slice a copy of a list, or does it just reference the objects in the original list in memory? A slice of a list in Python typically creates a new list that contains copies of the elements of the original list, rather than just referencing the objects in the original list. However, there are some nuances based on the type of objects in the list. Based on slice behavior, when you're slicing like so to integers, the slice creates a new list, 2, 3, and 4. The new list holds copies of the elements from the original list, not references to them. In this case, the slice is a new list object, meaning it separates the objects in memory. meaning it is a separate object in memory. Modifying the list like appending an element to it will change the value, not the effect of the original list. Mutable objects. And if the original list contains mutable objects like lists or dictionaries, the slice will create a new list, but the elements inside the new list will be references to the same mutable objects in the original list. Oh, okay. So mutable versus unmutable in this case. They're saying that integers. So what does the term mutable mean in this case? We can override ints in slice copies, right? In the context of Python, mutable refers to objects whose contents can be modified after they are created. In contrast, immutable objects cannot be changed once they are created. Mutable objects are those values that can be changed in place, including lists, dictionaries, and sets. Immutable objects, on the other hand, cannot be changed once they're created. Integers, strings, tuples. For example, you cannot modify an integer directly. X equals 5. I cannot access, but I can override X. Overriding integers in slice. You can modify the integers in a slice copy because integers themselves are immutable in Python. However, when you change an element of the slice, you're not changing the original integer object in memory. Instead, you're creating a new integer object and assigning it to a new list. Slice and list. Overriding an integer in the slice. Yeah, okay. Mutable objects in slices. Hey MIT, I appreciate you coming in. Thanks so much for stopping by. Yo, what's up? How are you doing? It means we can change the term inside the list by making the variable assigned to the list need to be changed. I'm saying the context of the list, not tuple. Okay, cool. So you mean mutable? I'm having a little bit of confusion between the term mutable because we can assign, if x is equal to 2, we can assign x to 3, right? We can override the variable x to 2, but mutable, you can't physically change the number 2, right? Is that what it means? Like you can't change a number 2 to anything. Like it doesn't exist, right? But we can make a new list in like a different order that is technically mutable, right? Or we can take a slice. Like a string, though, interesting. But for like a string, I guess you can't like physically change. But I thought strings were mutable. Like you can iterate over a string, can't you? And you can access indexes of a string. Immutable are integer strings and tuples. I thought we can index into strings and change. You're right to think about indexing to strings, but Python strings are immutable, which means you cannot modify them in place. While you can index into a string to access individual characters, you cannot change those characters directly. Okay, so you cannot override using indexing, like mutable indexing. Got you. Got you. I equals 1, 2, 3, 4, 5. I input 4 is equal to 6. Now if you print I, it will give you an output I equals 1, 2, 3, 4, 5, 6. Yeah, you can override the integer in the list. The list is mutable, but you can't change a single. Okay, got you. Thank you so much for your help. I appreciate you coming in and helping out. Okay, the same semantics is demonstrated when making a new list as a copy of an existing one with a syntax such as backup equals list primes. So this produces a new list that is a shallow copy in that it references the same elements as in the first list with mutable elements that is not this point is moot. In the contents of the lists were of mutable type, a deep copy, meaning a new list with new elements, can be produced by using the deep copy function from the copy module. A shallow copy. So if we call shallow copy. A shallow copy refers to creating a new object but not recursively copying the objects containing within the original object. Instead, the shallow copy simply copies references to the original objects, meaning that the nested objects or elements are still shared between the original or copied object. In Python, you can create a shallow copy of a collection, such as a list, dictionary, or set, using the method copy or list constructor in the copy.copy function of the copy module. So if we have original list is this, we call shallow copy list we call it on the original list. We call index 1, and we call index 0 from there. We get 99, and we set it to 99. Okay, so if you call list on an already established list, it creates a shallow copy of that list where if you mute objects in that list, they are reflected to the original. So shallow copy. Interesting. Awesome. All right. Where are we at here? Okay, I'm gonna finish this page and then we'll see what from there. Okay. In the context of lists were of a mutable type, a deep copy. If the context of the list were of a mutable type, a deep copy, meaning a new list with new elements, can be produced using the deep copy function of the copy module. As a more striking example, it is common practice in Python to initialize an array of integers using a syntax such as counter equals 0 times 8. This syntax produces a list of equal length with all 8 elements being of size value 0. Technically, all 8 cells of this list reference the same object as portrayed in figure 5.7. Okay, so 0 is the object and it is placed inside of and is referenced in all of the cells. Because 0 is just a object used in the characters, right? Okay, in the int class. At first glance, the extreme level of aliasing in this configuration may seem alarming. However, we rely on the fact At first glance, the extreme level of aliasing in this configuration may seem alarming. However, we rely on the fact that the reference integer is immutable. Every command, such as counters 2 plus equals 1, does not technically change the value of the existing integer instance. This computes a new integer with value 0 plus 1 and sets cell 2 to reference the newly computed value. The resulting configuration is shown in figure 5.8. So although we reference this same object, this object 0 is an integer. It is immutable, meaning that if we change it, we can only increment up and change it to 1, and it becomes reference to a new object entirely of integer 1. As a final manifestation of the referential nature of lists, we note that the extent command is used to add extend. Okay, now the extend command is used to add all elements from one list to the end of another list. From all elements used, we note that the extend command is used to add all elements from one list to the end of another list. The extended list does not receive copies of those elements. It receives references to those elements as portrays the effect of a call to extend. We hit 500? No way. No way, dude. What? No way. Let me grab my phone. I gotta take a screenshot of the channel before we go up one more. Hold on, nobody move, nobody move. Uh, Hopefully we don't go up. Oh, we went up by one already, you guys. You guys are fast. I was gonna take a screenshot. Oh, at 500. Well, nobody unsub, I guess. We don't need to go backwards, but that's funny. Thank you guys so much for 500. Holy crap, that's incredible. Like think that's like a graduating high school class, like a large graduating high school class, all supporting and watching and working together. Like we've created something really cool here, and so you know, you guys are just like honestly, you guys, we've created something really cool here, um, and I can't wait to see where this grows and where we grow as a programmer, where you grow as a programmer. You know, together, the type of projects that we could eventually make together. It's just going to go up from here. It's just going to we're only going to learn more, right? So, yeah, thank you guys so much for supporting me and also supporting yourselves through putting in the time to study and follow along and do the practice problems alongside me. You're only making yourselves better, right? Watching these streams and it's just it's positive, right? So thank you. You guys are great. Oh my gosh, that's crazy. Let me I'll do this. I'll do a screen. I have it pulled up here on my Safari so I can screenshot this guy. And it's still at the 500. I haven't refreshed yet on here. Okay, let me screenshot this. Like so. It took us 73 videos, it says I have uploaded. So I bet I only have probably like what, maybe 15 videos, but so I probably have almost like 60, 55 streams. That's crazy. Come a long way, you guys. Only go up here. 500. Woo! Thank you guys so much. You guys are the best. I love coming on these streams and talking with you guys. It makes things so much better. We need to save. 500. Save. Cool. We will post that in the Discord. So also, guys, if you want access to all my study resources, including the PDF above me, all my code, all my projects, all my all behind the scenes access to everything I'm doing, all my PDFs for the books, Python crash course. It's all in the Discord below, and I've really tried to make the Discord a cool place for us to have like everything kind of outlined for learning. Okay, you guys, it is 10:30. I hope for 5 million in the future. That'd be crazy. 5 million, no way. That's crazy. I really appreciate you guys joining me today. It was a lot of fun today. We finished chapter 4, practice problems. This one was pretty tough to work through, but we were able to get through it. We also did we worked on an extra problem in chapter 4. We did another example here, and then we started chapter 5, which is on arrays and getting into data structures and everything. I thank you guys so much. Again, I say it over and over again, but I mean it from the bottom of my heart. Thank you so much for being here. You're spending the time, which is extremely valuable. Your time is money, right? So thank you so much for being here. And I'll be back tomorrow, like I always do, 7 p.m., maybe 7:30 p.m. PST tomorrow. I'll see you guys back here then, and we will continue on with chapter 5 and dive into. Hopefully, we'll save some time tomorrow to get into our project. Yeah, tomorrow I stream every day. Hope I try my best. I do my announcements in the Discord, but I do try to stream every day from around 7 p.m. PST to 9:30, 10:30, sometimes 11 if I'm really really feeling it. But like I said, I am a chemist in my profession, so I do have a 9 to 5. So I am putting in quite a long days here, but I really enjoy it. I'm getting a lot out of it, and it's a lot of fun. So I'll see you guys tomorrow. Thanks so much for the support. Join the Discord down below, and I'll see you guys. Keep coding and keep learning. See you guys tomorrow.